Our next speaker is Zach Seibers, and Zach will present design and performance considerations of graphene-laminated thermoplastics for electrically conductive applications in space. Zach, you have 10 minutes.
Excellent, thank you. Can you confirm that you're seeing the slides?
Yes, sir. Awesome.
Yeah, so thank you everybody for joining me this afternoon, or maybe closer to lunch, depending on where you are in the world. I'm excited to be here to talk about some electrically conductive composites we've been working on and some of the applications we think they might be useful for in space. So first of all, I want to highlight the unique nature of this program it straddles the interface between material science and space exploration, and that's enabled by the REVEALS research program, where we look at a lot of different research areas, from astronaut HUD systems, which I don't think is being talked about at this particular gathering, but has been in the past NESF meetings. We have some ideas or research going on around novel radiation shielding composites, scalable embedded neutron detectors, and then finally the work I'm going to talk about is just this class of electrically conductive polymer composites. And so the reason that we are interested in this research is that we're very motivated by this static charging issue that is intrinsic to any material that's not electrically conducting, which includes pretty much all polymers that have ever flown into space. It also has, and as an example, I won't cover these in detail in this talk for brevity, but I would draw your attention to the Eureka STS-57, where you can see this photovoltaic cell that is shorted out electrostatically, and it led to real mission problems. There are also concerns related to lunar dust. I'm very fortunate to have been placed in this order after somebody who went into so much detail about this. But as you might imagine, having an electrically conductive surface can present some design strategies in dealing with this issue. And then finally, we care about polymers in general because they're generally good at radiation shielding, especially for their weight. So if we can overcome some of these risk factors, such as not being conductive, then it makes them more useful in general. And the way we do this is use a type of modified reduced graphene oxide. And reduced graphene oxide is kind of a graphene analog. It's not as conductive as pristine graphene. It has defects, but it's much more scalable. And so what we can do is take this reduced graphene oxide, we chemically functionalize it. This process is covered in detail in these two publications and cited here below. But as you can see, we can create these dispersions in a variety of solvents, and we can use these dispersions to coat plastic materials, which we then perform various post-processing procedures on. And that leaves us with a substrate that looks like this up here in the top right. And this is actually an older sample. I'm showing you a rougher one. It's one of the better, easier images to see good parts and bad parts. And if we look at these bad parts, we can see that it's quite rough. And in this SEM here, you can see that while the sheet resistance of this material is less than 20 ohms per square in general, there are these void structures. And when we think about, that has implications when we think about lunar dust and space applications. So the key features of these films are that we've got a scalable and very electrically conductive solution to the problem, but we have this roughness issue. And that's what I'm going to talk about in these next few slides. So when we think about these samples, there's a lot of ways you can see the roughness problem. And so in these samples that I'm showing you here only vary in the amount of coverage that was applied to the substrate. And then also, I just want to point out that all of these are on a PEEK substrate. So PEEK is a polyether ether ketone. It's an aerospace grade plastic. So you probably don't have any of this in your home, but if you think about a material that you might want to manufacture a plane part out of, or certainly parts of a spacecraft, PEEK would be a material that you might consider. In the far left, we have optical images. The middle column here is scanning electron micrographs, and then on the far right, we have profilometry. And in all three, it's pretty easy to see that there's a big link, or there's a big change in roughness with the amount of material that we have here. And then also it's variable. So if you look at this middle column here, it's very inconsistent when we start adding a lot of graphene, and that's due to issues with the melt processing procedure that I'm not going to cover in great detail here. And then we'll come back to these profilometry images, so just kind of keep that in mind. So to the lunar dust issue, and this is, again, I'm very grateful in the order in which we've presented here. The voids on this surface are a very big potential problem, we think, into using this type of a coating on a material in space. If you look in this figure A here, this is the size distribution of lunar dust collected during the Apollo missions. And there's a region here that's sub, 1 micron. So this is in the nanometer scale range. So basically these dust particles, there's a vast population of dust grains here that could penetrate these voids, and they get in there and they break up the surface. And so on the one hand, we have an electrically conductive surface, so we can get rid of the statically charged particles that we would expect to see in operations on the lunar surface. However, there's this size exclusion issue that we haven't really tackled yet. And so to kind of explore this ourselves further, I've done some research with a colleague, Micah Scable, who's also part of the REVEALS program. His research looks at various aspects of simulant dust performance, and mainly in more bio-focused molecules. However, he is helping me out in looking at my coatings as well. And so here we have an apparatus where my sample can sit in a tray and it gets charged dust grains dropped onto the surface. We can charge these things through tribocharging, so just vibrating the surface, or we can use an electron source, depending on the experiments that we're running. Very quickly, if we look at these samples, here are the profilometry scans that I showed you previously, 2 of the samples. And if we expose those samples to charged simulant dust, we can quickly see that there's a big difference between the amount of dust that's on the surface and then the roughness, and the starting roughness of the laminate layer. Not only is this readily apparent in the profilometry scans, and I apologize for the difference in units here between nanometers and microns, but the red and blue are still orders of magnitude high and low, so the pictures are still somewhat descriptive. But we can also see it just optically. When we take a picture of these are relatively small samples, but when we look at the intensity of the grayish white color here, that's the dust that's stuck to the surface, even after it's been removed from the vacuum chamber. The gray is much more intense in the rough surface rather than the smooth. And we also see a pretty big change in the sheet resistance of these materials, although I will note that both of these are still fairly conductive and would be able to serve any other purpose that we might design them for. And so a lot of work has gone into this. This will be a focus of a later publication, but given the 8-minute talk, I just wanted to draw your attention to it in case it piques your interest. We are considering different processing options such as spray coating, and then we've taken a closer look at some of our melt processing. Sorry about that. Some of our melt processing steps to form these nice uniform coatings. And so this is more this is more representative of what you might see laying around our lab and that's being used in our proposals these days. So much smoother, much more uniform, and with similar sheet resistances. And this is a picture of polyethylene just to show you something different than PEEK. So this can be applied to a variety of thermoplastic materials, which is why we like it. And so just as an example of a different application that you might consider these things for, we want to think about different applications. And they actually serve pretty well as joule heaters. And so we can think about this as de-icing, or you could even imagine the same principle, melting a frozen volatile in ISRU type applications. You can use these conductive joule heaters as a means of setting up thermosetting materials, which could also be incidentally used in like repair schemes on the lunar operations or in space. You have a viscous thermoset epoxy, apply current to the material, heat it, and it would fuse any damaged areas. And then finally, you can use this as an indicator that damage is occurring in the surface. And there's a big field that's really popping right now with examples of various groups looking at joule heating performance as a function of material strain or an inherent damage to the surface from a variety of sources. And so again, to quickly frame this in this work, this work is ongoing. We have been able to reach 100 degrees Celsius at only 20 volts. This is on an older sample, this image here. But this is really nice because this is a fairly large substrate, so 7.5 by 15 centimeters. And we're able to boil water off of it, which is nice and provides a lot of opportunities in a variety of space exploration use cases. And so Just to briefly summarize, we started off this venture with thinking about static charging, and we've ended up beating the performance we needed to do this by at least 10 to the 6 ohms per square. And then we're looking at lunar dust mitigation concepts. So right now, these are early stages, but we hope to transition to schemes using more advanced systems like an EDS system that you would conventionally see from NASA. We've talked about joule heaters, and then of course, like I briefly mentioned at the beginning of the talk, the graphene is also being looked at in EMI shielding and real-time dosimetry cases. And then we could also envision these types of things in structural monitoring. So you really have a one layer kind of does a multitude of operations, or at least has the potential to. With that, I would like to thank the Survey Institute and NASA Reveals that's funded this work and helped facilitate it. The John Reynolds Research Group, where I've done most of the synthesis and the material handling, and then a variety of people that have helped to make this project possible in one way or another, listed here at the bottom. So with that, I'll take the remainder of my time to take any questions, if there is any.
Thank you very much. Very interesting talk. We're over time, so we're going to move to the next speaker, and I'll hand it off to my co-chair.